All right, hello and welcome back, everybody. So we are moving on to section 9.2 and 9.3, where we'll be talking about actually solving some problems with the Laplace transform, seeing why it's useful. And so I want to comment, I'm going to shift up just a bit. This is, you can see in this remark, 9.1.12. These are our steps. Okay, so all of today, and really for the next sections as well, we want to think about, this is how you solve problems with continuous transforms, is with these steps. You're going to take the transform both sides of the equation, collect all terms, with like the unknown function onto one side and factor it out. You then have a symbol against that thing that you don't know what it is, and then you invert the symbol, and you finish by inverting the transform that you started with. So we're going to go through that here and see maybe how we could do that for a system of ODEs in the first case. Right, so this is a system that you would be able to solve with your exponential matrix. You would have to convert it to a first order system to pull that off. You'll notice here that I have two derivatives. So you would have to convert this to a first order system, but it will be autonomous, so then you can actually solve it with the exponential matrix. But it might take you a little bit of work to go through all of that to actually get it solved, and so maybe we can try to approach this with the Laplace transform instead and see if we can get our answer a little bit earlier. Okay, so here we have an IVP. It's given to me in 2 dimensions, and so it's going to be to my benefit to rewrite this in 2 dimensions. So as a 2D vector equation. So as a 2D vector equation, this is like my y vector, prime, double prime actually, and then I have -1, 1, 1, -1, y vector plus now the vector 1, -1. I don't like how that looks there. And my initial condition here at 0 is 1, 1. And the first derivative of the initial condition is 0, 0. So that's how I would convert it to a matrix vector equation. This is going to make my life easier if I'm taking a Laplace transform. There you go. You can see me rewriting it as a matrix vector equation. And then, okay, now we're going to follow our steps with the Laplace transform. So I'm going to take a transform of both sides. Okay, so you're going to start to see some weird things show up, and I want to talk about where they came from. So if I take a transform. So if I take the Laplace transform of y double prime, why does it end up with s squared capital Y minus s times the vector 1, 1? Well, we want to jump back to the fact that derivatives, the symbol of the derivative to the nth power. You'll recall that the symbol was s to the nth power times my transform, whatever the transform was, but then you subtract the initial conditions. Right, and you can go to the table at the end of the book for that, or you can go up a chapter or a section and find that. So you have the Laplace transform show up, but you pick up these initial conditions. And in particular here, those initial conditions are, I'm going to pick up an s times that condition. I'm going to pick up an s to the 0 power, s to the first power, s to the 0 power times the initial condition 0, 0, but thankfully the initial condition 0, 0 is 0, so I can leave it out of my equation, and I end up with, yes, s squared, that's this term here because it was d squared, but I also end up with s times the initial condition. And then the transform doesn't care about my matrix at all, but the transform will take lowercase y to capital Y. And here I need to be a little bit careful because it doesn't care about the vector, but it does care about a 1 sitting next to the vector. It cares about the hidden 1 here. Okay, so we've got a hidden 1 next to that vector, because I'm asking myself, what is the function that's multiplying that vector? And if I go to the table tells me that the transform of the constant function 1 is 1 over s, and so that's where the 1 over s is coming from. So this is where we're getting the transform of both sides. I then want to, by following steps, I'll mention that here, I want to isolate capital Y. Okay, so at this point, what I want to do is everything I can to isolate capital Y. And it shouldn't be that hard to convince yourself that the way to do this is to move every term with capital Y to the left-hand side. And you'll notice instead of putting a negative in front of the matrix, I brought it inside of the matrix. And so I've moved everything to the left-hand side, and I also gave myself s squared times capital Y, I gave myself an identity matrix there. So once again, there's a hidden 1 here, and I've given myself the identity matrix. No harm, because now if I distribute this matrix and that matrix, I get exactly everything with the y on the left-hand side. And then I'm going to move this term to the right-hand side. That's why I have s times the vector 1, 1 on the right-hand side. Okay, now I've isolated y to the left-hand side and everything else to the right-hand side. The only thing that's sitting around is I really want to isolate capital Y truly, so I need to invert this and bring it to the right. So I'm going to invert, I'm going to consider that as one giant matrix. I'm going to add it all together, and then I'm going to bring it to the right-hand side. So if I do that, so I bring it all together, and then I invert it, and it looks kind of ugly, right? So I've inverted it, I've brought it up. So the inverse matrix just looks like it's this, but then there's an s squared plus 2. That was my original determinant. So that's the matrix inverse divided by its determinant, or the whole thing is the matrix inverse. But this is like me swapping a and d around and making b and c negative and then dividing by the determinant. So there's my matrix inverse. There's my matrix inverse. And I guess I think there's an s squared in the determinant as well. But if I bring the matrix inverse around, act it on the vector, and I collect all my terms, I end up with a vector that looks like 1 over s plus 1 over s times s squared plus 2. And then I have 1 over s minus 1 over s squared plus 2. So really what the Laplace transform has done is it's let me isolate capital Y, which you'll recall was just the Laplace transform of my lowercase y as a vector. And it's let me isolate it, and it says whatever solution, whatever is solving this differential equation, I know that the Laplace transform of it looks like this. It looks like this vector. And so if we can invert this, under L inverse is what I mean by that. So invert the Laplace transform of that, then we find our original solution. So let's go through some work to figure out how to invert that. I think I might have, just given the inverse there. So I won't talk about that yet. Let's talk about how to actually invert these. And maybe I'll head over to the whiteboard for that. So let's say compute L inverse of my first term, which is 1 over s plus 1 over s squared plus 2. I want to find this and this in my Laplace transform table. So I say find these in transform table. So hopefully I can find 1 over s, and hopefully I can find 1 over s times s squared plus 2 in the transform table. So if I go all the way to the table, here we are. These were specific functions, right? So I'm going to be looking in the second section of the table. And 1 over s is there. It says that the inverse transform, so 1 over s is the transform space. If I invert it, I go to 1. So that's not too bad. If I head back here, I got the first one. This goes to 1. Now I'm looking for 1 over s times s squared plus 2. And if I head to the table, do I see 1 over s times s squared plus 2 anywhere here? I do not. There are no 1 over s times s squared plus 2's here. So this is what I mean when I said earlier we have to be clever and manipulate 1 over s times s plus 2 to look like, or s squared plus 2 to look like something in this table. And there are a few ways I can go about doing that. I can either jump up here and I can try to force the 1 over s to look like something up here. And upon immediate inspection, I don't really see multiplication by 1 over s anywhere up here. So I have to do something that's a little bit more clever than that. And if I jump back here, I ask myself the question, can I write 1 over s squared plus 2 as some combination of something over s and something over s squared plus 2? What is this notion? I think a couple of you are starting to recognize this. This is partial fractions. So can I compute partial fractions on here? The answer is yes. It's not that hard to do. Let's just recall how to do partial fractions. We're going to take that and consider it and try to start to rewrite it in terms of that. To do that, I would have a s squared plus 2 divided by s squared plus 2. I'm just multiplying. I'm finding a common denominator here. bs over s squared plus 2. Oh, sorry, I need a b plus c. This is partial fractions after all. bs squared plus cs over s times s squared plus 2. And now if I add those together, I have a plus b s squared plus cs plus 2a all over s times s squared plus 2. And you'll recall what I want is that I need this numerator to be equal to 1. And that tells me immediately that c has to be equal to 0 because there's no s's in the numerator here. So So I have c equals 0. It tells me that a plus b has to be equal to 0 because there's no s squared terms in my original case. A plus b is 0, which is equivalent to a equals negative b. And I know that 2a has to be 1. So 2a is 1, which means a is 1/2, which means b, which happened to be negative a, is negative 1/2. So I have a, b, and c, and so it turns out that 1 over s times s squared plus 2 is actually equal to a over s, which was 1/2. We'll call it 1/2 times 1 over s plus bs plus c over s squared plus 2. B, you'll recall, was 1/2 s over s squared plus 2. So I actually have this as my second term. The question becomes, can I find either of these? So find these in the transform table. I couldn't find this in the transform table, but that happens to be this. And can I find these in the transform table? I definitely can. I've already seen 1 over s that transforms to 1. Can I find s over s squared plus 2 in the transform table? We have it right there where I was drawing. S over s squared plus lambda squared. If it's s squared plus 2, then lambda is going to be root 2, right? So lambda is going to be root 2 there. So now if I scroll all the way up to my original solution to this Laplace transform problem, my solution, okay, I wrote it as sine of t over root 2 squared. I used the half angle identity on this, okay? So this is really root 2 over 2. So if I jump back to the whiteboard, let's give myself some room here on the whiteboard. If I take the Laplace transform of this, I end up with a 1. If I take the transform of this, I end up with cosine of root 2t. There's a 1/2 that comes along for the ride. There's a 1/2 that comes along for the ride. Okay, this is a half angle trigonometric formula for that. So really just the sine squared term, because the other term, the 1 out front, comes from right there. So I have a half angle identity that I've used there to simplify my solution a little bit. And of course, the only difference in the second case is that my plus sign turned into a minus sign. So all of a sudden, I've actually found the solution to my original ODE based off of the Laplace transform. All right, so we're going to move on to section 9.3, which is now kind of the main reason we use Laplace transforms, because I mentioned everything up here could have been solved with your exponential matrix. So if you wanted to go through the work to do this with the exponential matrix, you certainly could have. And you would have got the same answer. I mean, it's pretty clear that you can get sines and cosines in exponential matrices. But we have this ability to solve non-smooth initial value problems. And what do I mean by non-smooth? I mean, at least in this course, we're going to think about this as piecewise continuous, which means discontinuous at finitely many points. So we're going to have functions that are discontinuous at finitely many points, and we're going to actually be able to solve differential equations against those functions. So to start here, I want to talk about the Heaviside step function, or some people will call it the unit step function. And I'm giving it the name capital H. Most books with Laplace will use u of t minus t naught, or even u sub t naught of t. And there I put it there, and they'll use that for unit step instead. And then if you get into like PDE's territory, they like to say Heaviside instead. So just be aware that you can use either of these. The Wolfram language uses Heaviside theta, because sometimes actually it gets used as a theta t minus t naught. So a lot of these things are interchangeable, and there's not really a common notation here. So we just have to be slightly aware of it. But what is this function? It's a piecewise function, right? It's piecewise. And it's simply equal to 0 below t naught. It's equal to 1 once you've made your way to t naught. So here I am. I have 0 over here. I jump up to 1. Where's that vertical portion? That's exactly at t naught. So it's just a function that's 0 over here, 1 over here, and it flips at t naught, whatever t naught happened to be. That's my x-axis. So it's useful because this is what we have the ability to construct all other piecewise functions from this. can use this as a quote-unquote basis. It's that's an abusive notation, but basis for piecewise functions. Okay, so really that's why we have a useful function here. It's really a basis for piecewise functions, and I'll show you why. I'll show you why right here. So the proposition 9.3.2, Heaviside representation of piecewise functions. So let f be a function which takes some values over intervals, right? So I have t less than or greater than or equal to tj, and it's less than tj plus 1. My function takes the values on those intervals, okay? The value f sub j. So like for example, like a good example of this would be the function cosine of t is less than -1, sine of t is greater than or equal to -1. I mean, it's a perfectly valid function. This is like f1 is like cosine t, f2 is like sine t. And then you construct your intervals in which it has those behaviors. Anyway, given that piecewise function, there is the representation in terms of the Heavisides. So all you do is you extract the lower bound, take the lower bound tj, and you shift the Heaviside by that. You take the upper bound tj minus 1, and you subtract off the Heaviside shifted there. So this is kind of like your little square that's sitting equal to 1 over this interval, and it's equal to 0 everywhere else. You multiply that by the value of the function on that interval, and then you take as many sums as you need to take sums. And the proof, it's the exercise. It's not that hard to do, but you'll get to do it. So here's a really interesting thing. If we're using non-smooth functions in differential equations, what does it mean to take the derivative of this thing, which you'll recall was 0 and then it was 1. 0, 1, t naught. If I take a derivative of that, it should be 0. Derivative should be 0 here. The derivative should be 0 there. It's constant. But what should the derivative be right here? What's my rise over run? Rise over run. Well, the rise is 1. The run is 0. This is like a positive infinity. Question mark, right? So it's like it's a weird thing that always has to get introduced in differential equations. There are ways to make this formal. This is not a true equal sign, right? 1 over 0 is undefined. And yet there's an understanding that if we say that the derivative of the Heaviside function is equal to infinity, there should definitely be a 0 there. Here is definitely 0. If we say that the derivative of the Heaviside function is equal to infinity at the point at which it changes, we gain some useful information. And there are ways of making that mathematically rigorous, but that's the idea of these called distributions or generalized functions. We don't have time to get into that in this course. Actually, it's a graduate level topic to get into. So we can't really get into that idea in this course, but you in many ways can take a derivative of this Heaviside function. And in many ways, the derivative takes the values 0, infinity, and then 0. So let's observe how we might take the Laplace transform of this Heaviside function. And we'll just do this by definition. We just plug it into the Laplace transform. By definition, the Heaviside only turns on once you run into t0. And then so you integrate e to the minus st from t0 to infinity, and you get the following result. You get e to the minus st0 divided by s. And so the Laplace transform of the Heaviside function is perfectly well defined, which makes a lot of sense because the Heaviside function is a function. But what gets interesting is that the Laplace transform of the derivative of the Heaviside function is also perfectly well defined, right? And this is where we start to get into this in between mathematically rigorous and not mathematically rigorous idea, where the left-hand side, this derivative is not actually computable. You can't finish this derivative here, and yet on the right-hand side, if we multiply a Laplace transform of something by s, that's equivalent to taking a derivative inside of there, and there's nothing that says I can't multiply e to the minus st by s. So we do actually get a well-defined Laplace transform of the derivative of the Heaviside. What we don't get is a well-defined derivative of the Heaviside. So it's really interesting that we can be well-defined in Laplace space, but not in regular space. It turns out if we try to compute L inverse on this to try to understand h prime, computing L inverse on this gives me the following integral, which actually doesn't make any sense. But it does make sense if I compute it against the Laplace transform of f, because if I compute it against the Laplace transform of f, all of a sudden I have a transform and its inverse. This is the inverse transform showed up. If I switch the bounds on the integral, what I end up with is that the transform against the derivative of the Heaviside function just extracts the value of the function at t naught in some sense, right? So this integral extracts f at t naught. Whatever that derivative means, we don't really know what it means, but whatever it does mean, it extracts the value of f at t naught. So that's really something interesting to think about. And so we give this a name. We call it the formal derivative of the Heaviside function. And it has the property, formal, right? And it has a property called the sifting property, where it sifts, if I integrate against it, I sift the function at the point t naught. And actually, we give the derivative a name. The derivative is called the Dirac delta. I'm putting this in quotes because I don't want you to go around calling it the Dirac delta function, but everybody else does. So this is the Dirac delta, quote, function. And it's not a function, it's a generalized function or a distribution, but it's equal to the derivative of the Heaviside function at t naught. So I have 0, infinity, 0. In some sense, this looks like a needle. There's your x-axis. This is t naught. So the delta function looks like a needle that's infinitely tall and infinitely thin. An infinitely tall, infinitely thin needle. And it has the property of the sifting property. So we want to think about, hey, this thing I'm calling the delta function, if I integrate it against f, I'm going to recover f at t naught. Okay, so going through a lot of work just to establish how to compute these ODEs with non-smooth coefficients, I have to cover one tiny other thing, and that's the continuous convolution. So I have this definition showing up called the continuous convolution. We had an exercise on the discrete convolution in the previous section. In terms of continuous functions, given two functions, they map some set into the complex plane. The continuous convolution of the two of them is defined by taking one function and taking the other one and reversing it and shifting it. Okay, so I have a function of tau. I have some variable t that I'm keeping around, and then I'm shifting that second function by tau. I'm going to integrate over all of my space against tau. And what that's going to do is it's going to integrate away that and that, right? Those all go away, and I have some weird function of t left over. So I have a function of t left over, and that's what I'm going to call my convolution. I'm going to give it the name star, because it is actually a binary operation, the same way that multiplication, addition, subtraction, and division are binary operations. And so I start with two functions, and I can convolve them together, and I end up with yet a new function. Now, that's kind of the formal definition. I'm going to scoot down to how this gets defined in the Laplace transform sense. Okay, so in the Laplace transform sense, this is the Laplace convolution. So if I convolve two functions f and g in the Laplace transform sense, I take the integral from 0 to t of f of tau, g of t minus tau, d tau. So this is what I want to think of when I'm in this course for Laplace convolution. And I have the following properties. I have that it's commutative. So it behaves very similar to multiplication. It's commutative, it's distributive. You can see this is right distribution, but it's also left distributive, so it doesn't really matter. So it's commutative, it's distributive, and then why does it really behave like multiplication? Well, that's right here. It really behaves like multiplication because if I take the Laplace transform of a convolution, I actually gain true multiplication on the backside. So that's super useful. True multiplication in Laplace space if I start with a convolution of two functions. This is a proof that you'll have an exercise on, so I'm sure you're looking forward to that. So you can also understand item 3 here being that the Laplace transform of a convolution is the multiplication of both of them separately. This could also help me invert, because I'm taking the inverse Laplace transform of two things that I individually know how to invert either of them in pieces, and then I can invert it using a convolution. So if I know the inverse of f, I know the inverse of g, and they happen to be multiplied, then I can compute the overall inverse by computing a convolution of f and g. All right, so finally we're going to get into this case of solving an IVP with non-smooth forcing function. So here I have an IVP. It's perfectly well defined, but the forcing function is stuck on the right-hand side switches. It changes behavior at t equals 5. So once I get up to t equals 5, I shift from a forcing of -1 to a forcing of +1. This is incredibly useful since it mimics flipping a switch. Okay, so if I'm thinking along the lines of electrical engineering, this is so useful in electrical engineering, because every time I have a circuit board, if the voltage on one transistor gets large enough, then all of a sudden it flips and you get something new in the entire circuit. So if I'm modeling the circuit, these sorts of interactions happen all the time. So So this is very important, but I have to use the techniques that I've developed so far to be able to compute the solution. So what are those techniques? Well, the first technique is my representation of this. Represent this as a sum of Heaviside functions, right? If I can represent that as a sum of Heaviside functions, then I know how to take the Laplace transform on both sides. So first step is I'm going to rewrite the right-hand side now as -1 times the Heaviside on each bound, right? So maybe I'll put this in. There goes there, there goes there, and the -1 goes out front. And then the same thing happens on the second term. I have a +1 out front, I have a 5 there, and I have an infinity there. And let's just talk really briefly. What is the Heaviside function shifted to the right infinitely far? It means it's equal to 0, and it finally spikes at infinity. But the function which spikes at infinity is equal to 0 everywhere. Okay, so this actually is equal to 0. So you really don't have to represent that there if you don't want to. But now I have y double prime plus y equals some combination of Heavisides. And actually, if I simplify this a little bit, the Heaviside at t minus 0, this is the function which bumps up right at 0, but the Laplace transform, and actually this entire function, is t greater than 0 because it's in an IVP. Right? So I'm only talking about the future, which means that this function is actually equal to 1. So you can keep them around if you want to, but it's not the end of the world to get rid of them either. So if I simplify the right-hand side, this whole term can actually simplify to -1 plus 2 times Heaviside of t minus 5. And so that's really this ODE with the piecewise function on the right can be represented as an ODE now with the Heaviside function on the right-hand side. And I know how to compute the Laplace transform of the Heaviside function. The Laplace transform of the Heaviside function is e to the -5 over s, and then the 2 sits along for the ride. And so this is how we're going to start to be able to solve these non-smooth problems with the Laplace transform, is by converting the Heaviside, and we know how to transform the Heaviside. We get e to the minus t naught s over s. Okay, so that's where the Heaviside comes from under the Laplace transform. The -1, we should feel very comfortable with that. That maps always to 1 over s. The y double prime under the transform is mapping to, well, we have s squared y, but don't forget that the primes always give me some initial conditions as well, and then my regular y maps to capital Y. So that's how the Laplace transform sees everything in my original ODE. And if I want to, I can plug the initial conditions in there and there. And upon doing that, I recover s squared y minus 1 plus y is -1 over s plus 2 e to the minus 5s over s. And I'm going to isolate capital Y. Okay, so I'm going to bring everything with capital Y to the left-hand side. I'm going to bring everything else to the right-hand side, and then factor out capital Y. And you can see at this point, all I want to do is divide by s squared plus 1. This is me dividing by my symbol in many ways, right? So if I divide by my symbol, or invert my symbol, it's equivalent to me inverting the differential equation. And I end up with the following. I have 1 over s squared plus 1 minus 1 over s times s squared plus 1 plus 2 e to the minus 5s over s squared plus 1. Now, I'm not going to go through the procedure again because we're already getting long on time. But going to the table, you should recognize that this is sine of t. If I'm going to invert it, right? Once I invert everything, that's sine of t. This will invert similar to the last case. This is partial fractions. And I'm going to get something like 1 over s plus 1 over s squared plus 1. Actually, s over s squared plus 1. Okay, so this will go to 1. This will go to cosine. And then this term is a little bit trickier. If I go to my table, I'm going to jump down to the table now. So I'm multiplying. What does multiplying by e to the minus 5s do to an transform? If I jump down to my table, we can see, it's a long chapter, we can see multiplying by e, so e to the minus 5s, multiplying by e to the minus 5s shifts whatever my transform is going to be, my inverse transform, it shifts it by 5, and then I multiply by the Heaviside by 5. So this is going to be some sort of, let's see here, this is going to be some sort of shift by 5, and then whatever this 1 divided by s squared plus 1 would be, it's going to be similar to like cosine again, because we saw that this was like 1 plus cosine, this will be like 1 plus cosine or 1 plus sine, and it's just going to get shifted by 5. So if I scroll down, I can also compute this with convolutions if I want to. I end up with 1 minus sine minus cosine, plus 1 minus cosine shifted by 5, Heaviside shifted by 5. And so if you want to go through convolutions, you can calculate that with convolutions too. But there you go. That gives me the solution to the ODE. And you can see that the solution fundamentally changes at t equals 5 because I've added a new term in here, which is exactly what we expect when we look at that. The switch flips after 5 seconds. And once the switch flips, all of a sudden, I pick up this extra term of 1 minus cosine t minus 5 on the heavy side. So like this term shows up only at 5 seconds, which is flipping the switch. And if I plot those, you can see them plotted here. This is the original function, and then at t equals 5 seconds, which is right here, all of a sudden a switch flips, and then something new happens, right? And so you recover a smooth solution. That's the really interesting thing about these is you have non-smooth forcings, and yet our solution is smooth. And so that's something that's really useful about the Laplace transform. Anyway, sorry it's been so long. I guess I tried to shove 2 sections together when maybe I shouldn't have. But thanks for sticking with me. I'll see you in class. Bye.